Hello, and welcome to the 2023 Design Expo presentation for the Michigan Tech Aerospace Enterprise. My name is Seth Quayle, and I'm the Program Manager of the Aerospace Enterprise, and I'll be telling you a little bit about our enterprise, going over what projects we've been working on and what our plans are moving forward. The Aerospace Enterprise is a collection of undergraduate students that are collaboratively exploring the aerospace industry through various hands-on projects. The program is comprised of majors from all corners of campus working together to design, build, and test multiple small satellite platforms. The enterprise has two primary objectives, the first of which is to educate the future leaders of the aerospace industry by providing undergraduate students with hands-on space systems engineering experience. The second aims to advance U.S. space technology by solving real-world problems. Not only are these problems challenging, but they are directly relevant to current U.S. military and NASA needs. Students get to learn about satellite systems while also completing work suitable for the aerospace industry. Our program was founded by our academic advisor, Dr. Brad King, back in 2001. Since then, it has helped over 400 students obtain their undergraduate degrees from Michigan Tech. As of now, we are currently home to 84 active members from over 13 different disciplines across the university. We have two on-campus facilities that we operate out of, those being the clean room and the Aero Lab. We are also actively funded by two well-known satellite companies, which allowed us to successfully design and launch one satellite into space and support two more that are on the way. Speaking of the two satellites that are on the way, the Enterprise has two active missions, the Auris mission and the Stratus mission. The Auris mission is a pathfinder mission with a main purpose in exploring interference potential of geostationary satellites by mapping their RF emissions onto Earth and determining their locations in space. Stratus, on the other hand, is a mission focusing on using cloud image data in order to build 3D models of them to help with climatology and weather models. Now let's talk about these more in depth. One of the most recent problems in the space industry that our group has been working on is that over the past few decades, space technology has advanced such that satellites can now take up less space than a loaf of bread. The decrease in mass and volume allows for cheaper rides to space, meaning that the space environment is now more accessible than ever. This increased accessibility has led to thousands of new active spacecraft in orbit, creating significantly more traffic in space. As you may know this with vehicle traffic, having more cars around you on the road increases the risks of accidents occurring. This is also true for satellites, especially when it's difficult to be aware of other satellite activity. This increased traffic in space has created new risks for interference and has necessitated new methods of persistently monitoring the space environment. The Aerospace Enterprise's response to this issue is the Auris mission. So as I stated earlier, Auris is a pathfinder mission whose goal is to demonstrate a low-cost platform capable of exploring the interference potential of geostationary satellites. This mission will feature a small satellite comparable in size to a shoebox that will measure the antenna beams of communication satellites to further characterize their activity in space. Modern communication satellites can potentially create both electrical interference through interfering signals or create physical interference by colliding with one another in orbit. The Auris mission will allow us to explore both types of interference in an attempt to further the understanding of space domain awareness. So let's go ahead and talk about how we plan to do this. There are two main mission objectives for the Auris mission, the first of which is called beam mapping. The Auris spacecraft will be flying through the antenna beams of a target satellite, and as it does so, it will be using its onboard antenna to measure the power of the signals that are being emitted by that target satellite. After passing through the beam of that satellite multiple times, we will be able to stitch together these power measurements and create the contour plots that you see on the lower left-hand side of the screen. The other mission objective is called multilateration. As Auris measures the strength of the target satellite's signal, it's going to take a timestamp of when it receives that signal. Meanwhile, 3 additional ground assets will receive the same exact signal, but at three completely different times. Knowing the location of the four receivers, as well as the time in which they received the signal, it will allow an operator to backtrack to the source of emission. Having both location knowledge of a target satellite and a map of its outgoing signal will allow an operator to better understand the characteristics of a specific satellite in space and monitor its activity by just listening to its signals. Now, let's switch gears and talk about the Stratus mission. The Stratus mission shall demonstrate an inexpensive, scalable architecture capable of imaging clouds and generating usable data for validating and improving existing climate and weather models. This will be achieved through three primary mission objectives. The first of which is that the Stratus mission shall register each pixel to a location on the surface of the Earth with a fidelity adequate for research. The second of which is objects that are 1,000 meters apart or more with respect to the ground shall be discernible within an image. And then the third is that the Stratus mission shall determine the cloud fraction of images taken over land. Similar to the Auris mission, this mission has various points of motivation for its completion regarding aspects of cost, research, scalability, and education. This platform, depicted on the bottom right-hand side of the screen, is not only a sliver of the cost of a bus-sized satellite, but it also can be scaled upward to increase the frequency of data collected. Nonetheless, Stratus will enhance the current climate research efforts by offering affordable means of collecting cloud data, as well as offering students a means within our enterprise to get hands-on experience in space systems engineering and spacecraft operation. So that was a little bit about our missions, but how does an undergraduate student team actually design and build a spacecraft capable of doing said missions? The secret to designing the satellites is following the path of what we call space systems engineering, which is a concept of taking a project from its conception all the way up until its final stages. First, you determine the mission, or you plan what you're going to do in space. Then you define a list of requirements for the mission, which then guide the subsequent design phase of the spacecraft. After the design is complete, then you move to actually procuring and testing the hardware to specifications given by your prior list of requirements. Once the testing is complete, the spacecraft can finally be launched into orbit and begin its mission. So where is Auris on this timeline? Auris is currently in the testing and integration phase. After spending about 3 years in the design phase, these plans are finally coming to fruition, and we are taking action by ordering all of the design hardware, connecting them together, and testing their functionality here on the ground. And that's what the next year, year and a half will look like. As you can imagine, there are a multitude of different systems involved in a spacecraft, from an electrical power system to a multitude of sensors and actuators, a means of communication, and of course the hardware that is actually needed to perform the mission. This is what we call our avionics group, and it can be depicted by the group that you see in the table on the left-hand side of the screen. Currently, these groups are undergoing testing, from functional testing being component level testing all the way up to system testing, testing their entire system together in one. After the completion of this testing and integration campaign, the spacecraft can launch and begin its mission in space. This is expected to be late 2024 to early 2025. So for Stratus, due to the generosity of the Michigan Tech community and its network of alumni, the aerospace enterprise was able to raise enough money to continue the Stratus mission and get the spacecraft back to an operable condition. Michigan Tech Aerospace Enterprise has decided to start over, and we're working closely with vendors that we've chosen to create a successful platform for spaceflight. We are currently working to procure our hardware, and we will be expecting a launch around the same time as the Auris mission, late 2024 to early 2025, and this will be at the conclusion of our testing and integration campaign. We are currently undergoing hardware procurement, and upcoming projects include the continuation of our ground support equipment design so we can support our satellite here on the ground, and then testing all of our components once we get them in-house. We're expecting a prototype imager here in June, as well as an onboard computer around the same time. So with that, thank you. The aerospace enterprise would not be where it is today without the generosity of the Michigan Tech community as well as the support from the community. With any questions, feel free to reach out. And with any interest in our enterprise, feel free to take a look at our social media pages. Thank you very much.